Hello everyone. So we are in the last lecture of statistical thermodynamics. There are so many topics in this chapter, but these are beyond the scope of discussion in this series of lecture, because up to now the content that have been covered here is enough for the undergraduate students. So in future, if situation demands, then I may be back with some few more topics on this chapter, such as application of the Boltzmann distribution law, discussion on the fermions, bosons, so and many more things. Okay, evaluation of beta, so these things. But for now, up to this, it is okay. Okay, so in the last topic today, in lecture number 14, I am going to discuss ensemble, microcanonical ensemble, and Gibbs paradox. Okay. So let me start with components of partition function. So far, the partition function we are dealing with is actually the molecular partition function. Okay, and in the last lecture, you have learned about the molar partition function, where Z was introduced. Z was nothing but f to the power n0, isn't it? But the molecular partition function has also so many components. Let's see, what is this? Chemical systems are composed of molecules, and molecules are associated with energy of different types. So molecules are associated with energy of different types. So what are the types? Okay, any particular molecule may have rotational energy, okay, epsilon r, vibrational energy epsilon v, translational energy epsilon t, electronic energy epsilon e, and nuclear energy epsilon n. And if there is any more, then that is why I have used the term here etc. Because our knowledge is not absolute. Okay, beyond these five, there may be something else, isn't it? The debate among Sir Niels Bohr and Sir Albert Einstein still going on. The conflict between quantum mechanics and the theory of relativity. So these are going on. So many things can come up in future. So that is why this etc. is used. We do not know the absolute form of energy. Okay. So right now we are going to deal with 5 types of energy. Particularly out of this, nuclear energy will be omitted, because this is a large energy and it has a lot of difference with these 4. These 4 are mainly associated with motions of particles. Okay, and nuclear is something different. So in the next slide, in one part, we are going to discuss with only R, V, T, and E. Okay, nuclear energy will be omitted there. Anyway, so for these 5 types of energy, the corresponding partition functions, these are all molecular partition functions definitely, and but then out of these molecular functions, they are specialized as rotational molecular partition function. Okay, such as and vibrational molecular partition function this way, and these can be derived. Okay, there is another derivation which also is not derived in this series of lecture. As I have said, in future, if possible, I may be back with those lectures, but not right now. So since these are you will find that these are all multiplicative properties, and it can easily be derived that this molecular partition function is the multiplication or the product of these all components. Okay, so this is one part, components of the molecular partition function. Now in classical thermodynamics, you have learnt about extensive properties and intensive properties, and you know the definitions of them. The definitions of extensive and intensive properties are from the perspective of amount of substance. If the property is dependent on the amount of the substance or the mass of the substance, or then it's called extensive property, and if it is independent of the same, then it is intensive property. But here, from a different perspective, we are going to discuss this. Actually, macroscopic properties that are obtained, these are obtained by summing together from contributions from all the molecules in the system. Now you have little bit come to know that what is about summing, isn't it? You have several times used the term summation, isn't it? Sum over I, 0 to I equals to 0 to I. So these things So this is summation. So additive things, which things can be added, okay, or can be summed up, those properties are those macroscopic properties are actually extensive properties. For example, total number of molecules in the systems, n. Simply we just described it as by n. In our previous systems, n equals to, at our very first example, n was 4, isn't it? So likewise, n is the total number of particles in the systems, or total number of molecules in the system, which is a extensive property. Volume, total space occupied by the system, and energy terms. So this energy are the combination, mainly these energies, which can easily be derived experimentally in the lab. The rotational, vibrational, translational, and electronic energy. Okay, so their overall value. So if ni number of particles in the ith excited state of the rotational level, okay, ni number of particles in the ith excited state of the vibrational energy levels, similarly translational and electronic state, okay, then add the overall energy of all the particles by using this summation sign. So this is the energy. This is also an example of extensive property. Now the example of intensive property, the macroscopic properties that are obtained by averaging the contributions from all the molecules. So this is actually averaging of the summation. Okay, so this cannot change if the number or amount is changed. So this is simply average. Such as pressure. Pressure is the average force per unit area exerted by molecules in the system, isn't it? Similarly, n dash is the number density, number of molecules per unit volume, and it has the formula, you know, Pn0 by RT. You know all about this. Mass density, Pm by RT. Okay. Then chemical potential, G by N, where this N is number of moles. Okay. This small letter N is G by number of moles. Here in the previous slide, I have used one thing. This N, this small n, actually number of molecules, but this N in this line is actually number of moles. So do not just amalgamate them. Okay, distinguish. So this n and n, capital letter N, it should have been written as capital letter N then, isn't it? Here it should have been written as capital letter N in order to maintain the similarity. Okay, so you don't get confused. Anyway, that is not the point here. Actually the point is the chemical potential is what? The molar free energy is chemical potential. Okay, so these are all intensive properties. Now the question would come, why these classical thermodynamic properties like intensive, extensive properties are coming here? Okay, it is coming because we are going to introduce the concept of ensemble right now. Okay, what about this? Now F is known to you as molecular particle function, but this F is not applicable for non-interacting particles. In reality, some particles are interacting, very simple, real gas particles are interacting, or suppose the 2p4 electron, okay, 2p4 electron is interacting with the 2p1 electron, because their spin quantum numbers are always opposite. If it is plus half, then other one is minus half. Suppose think that 2p1 electron according to the Hund's rule in the px orbital, and according to the Hund's rule 2p4 electron is also in the for 2px orbital, isn't it? But they are interacting with each other, and their spins are opposite. So they are also examples of interacting particles. So this F molecular partition function is only applicable for non-interacting particles, but not for the interacting particles. So this would not apply to the interacting particles. In order to extend the statistical evaluation, that means what you are doing for the previous few series of lectures, statistical evaluation of thermodynamic properties of a system involving interacting particles, Gibbs invented the concept of ensemble. Okay, so this concept was introduced by Gibbs. So what about this? The definition and criteria of an ensemble. Suppose this is an independent system. Okay, this is another independent system, and here you can see several systems. So this is a collection of systems. Okay, and this collection of systems may be the same system at different times also. Okay, at t equals to 0, at t equal to 1 second, t equal to 2 seconds, the same systems may also be represented like that. Okay, that is why here a hypothetical term is used here. Okay, so the position and coordinate, that means coordinates and momentum are continuously changing of these particles, but their macroscopic properties can be measured. And what about whatever be its state. Okay, so ensemble is a hypothetical collection of a large number of systems, each constructed to be a replica of the system under study, and it should follow that the collection of the systems should be macroscopically identical, so that any three of their macroscopic properties are same. So here this point is important. Their macroscopic properties may be same, and depending upon which three macroscopic properties are same, they are divided into different ensembles. Okay, so ensemble is actually the collection of systems which have some similarity in their macroscopic properties, and the systems would be independent to each other. That means they are separated by some boundary. Now microcanonical ensemble, if the set of all the systems have the same energy, volume and number of particles, provided that they are isolated by rigid, impermeable and adiabatic walls. You all know about these three terms: rigid wall, impermeable wall and adiabatic wall. Adiabatic wall doesn't allow energy to pass. Impermeable wall doesn't allow a particle or substance to be exchanged within the system and the surrounding. And rigid wall means they cannot be torn, okay, or they are they are not soft like a wall of a balloon. Okay, so they are rigid wall. So then this is the example of a microcanonical ensemble. Okay, this definition may not be very much clear to you. Let me elaborate this with some example. Okay, now you know the entropy. This entropy is actually known as the Boltzmann entropy. Okay, and it has the expression, you all know about this, K, L and W. Now W in some books, and somebody also say denote it as ohm, this sign. Okay, but the thing is same. In some books you will find K, L and ohm. Okay, so both are same, but here I am denoting it as W. It is convenient to me. Anyway, this W is known as ensemble size. So the number of microstates corresponding to a macrostates were known to be the thermodynamic probability of the system, but actually this is the ensemble size if the system is confined to such a container where the overall energy is same, the number of particles is same, and the container is same. Definitely the volume is same by default, isn't it? So this system had how many microstates? This one had 4 microstates, this one had 12, this one had 6, this one had 12, and this one had only 1 microstates. So overall number of microstates were 35. So this is the ensemble size. Okay, and all these states are the collection of states of the same system. Okay, it can take away any one of them, and definitely it will try to get the highest number of macrostate macrostate which has highest number of microstate, that is ms2 or ms4. That is at equilibrium, but it may also take this macrostates also. But these are all collection of systems. These are the example. That means the collection of these 5 macrostates is the example of a microcanonical ensemble. Okay, so when we recall the very first example of particle distribution, where energy, that means 4 epsilon, number of particles, that means n equals to 4, and the volume V by default, definitely in the same container it is going on, so the volume by default should be same, were all fixed. This was the example of microcanonical ensemble, where the ensemble size was 35. Okay, so follow the very first lecture if you have forgotten. Now canonical ensemble, grand canonical ensemble, and isothermal isobaric ensemble. Okay, these are the 3 examples. As I have said, any 3 of the macrostates should be same. So here in the example of canonical ensemble, temperature, volume and number of particles should be same. Okay, in the grand canonical ensemble, temperature, volume and chemical potential should be same, and in the isothermal isobaric ensemble, temperature, pressure and number of particles would be the same. And now, before moving on to the last topic, the Gibbs paradox, we have to discuss a little bit thing, the Gibbs entropy. Okay, we know about the Boltzmann entropy, S equal to K L and W, and we have derived this expression entropy K equals to a natural log of n factorial product over I n I factorial. We know about this, and after that, after a long derivation, you have reached to this expression n K L N F plus n K T d L N F by dt, isn't it? So up to this it's okay. Okay, and this is definitely applicable for the distinguishable particles, but there is a Sackur-Tetrode equation where there is also another very long derivation where in terms of the mass of the each particle, temperature, you can get another expression of entropy, which is applicable for the distinguishable particles as well as for the indistinguishable particles. There are two expressions. One is for the distinguishable particles, it is n0k within bracket ln natural log of v twice pi mkt by h square whole to the power 3 by 2 plus 3 by 2. And for the indistinguishable particle, just v is divided by n0, and here instead of plus 3 by 2 it is 5 by 2. Okay, so whatever the physical significance is, n0 is the Avogadro number, k is the Boltzmann constant, v is the volume of the system, m is the mass of each particle, t is the temperature, h is the Planck's constant. So I think it would be very much clear to you. So if possible in future I may be back with this derivation of this Sackur-Tetrode equation also, okay, if situation demands. Now move on to the Gibbs paradox. Suppose, say here two separate systems, independent systems, which have entropy S1 and S2. There are particles, several particles, this blue dotted spots, and this pink colored line is the partition, and their initial entropy before mixing was S1 plus S2. Okay, and since entropy is an additive property, so if you remove this partition, then their combined entropy should also have to be S1 plus S2, and if S1 is equals to S2, then it is twice S1, isn't it? Now let me apply this into the expression of entropy of the Gibbs expression. Okay, and for the distinguishable particle expression, the initial entropy was this one entropy plus this entropy of this one. If S1 equals to S2, then it is twice S1. The initial before mixing them, that is means the entropy of the combined system when they are independent to each other. And since the expression is n0 etc., so just put a 2 here. Okay, then you will get the expression of the initial expression before mixing. Then what is the final expression after mixing? After mixing, the number of particles would be doubled, twice n0, and the volume would also become double, twice v. So in place of number of particles n0, it is definitely Avogadro number of particle, one mole of particle, you have to put twice n0, and in place of v you have to place twice v. So what is the final result? Now the final result is twice n0k ln twice v. This twice v is now separated as ln2 plus ln this part within the second bracket, okay, plus 3 by 2. So these two are equal. Look, initial value of S, that means before mixing was twice n0k ln, only v was here, isn't it? And in the final entropy expression, here is ln2, this x part is extra, isn't it? So this is greater than the initial one, so S final is greater than S initial, so delta S is not 0. So how can that be possible? It's a paradox, and this paradox is known as the Gibbs paradox. So we have to remove this Gibbs paradox. So move on to removal of Gibbs paradox. In order to remove this paradox, we have to consider the particles as indistinguishable. Okay, this is the trick. We have to consider the particles as indistinguishable and apply the second equation, okay, which was obtained from the Sackur-Tetrode derivation instead of being distinguishability. Okay, so now here you just add them. Before mixing the expression is this, and after mixing the expression is the same, isn't it? Here in place of v you have put twice v, here in place of n0 you have put twice n0, and here in place of n0 you have put twice n0. And these two was for two systems, but here only one system, so here is 1 to the left hand side of this first bracket, so that means nothing is there. So, but here in place of n0 you are putting twice n0. Actually this is the same, this becomes the same, twice n0k, here also twice n0k. Within the bracket here v by n0, 2 would be cancelled by each other, here v by n0. So S initial and S final would be same here. Look, okay, the final expression which is same as the S initial. Okay, therefore Si is initial entropy, and we started from S final and we have finished at S initial. So these two are same now. So delta S equals to 0, that is there is no change in entropy. Okay, therefore the Gibbs paradox can be removed if the particles are considered as indistinguishable. Therefore you have to attribute the indistinguishability of the particles in order to solve out this problem instead of being distinguishable. Okay, so that's all for this last lecture of statistical thermodynamics. Thank you, and wishing you all the best for your semester exams. Have a nice day.